Welcome to Lesson 26, Scatter Plots and Linear Models. Now this kind of builds on what we learned in Lesson 25 with linear models. We're kind of just building. Yeah, that's a good way to put it. So if you look at page 229, you see this lovely graphic representation here at the top of the page. And you can see the difference between what we just did and now. We've got all these dots. So instead of having just a straight line, now we're given actual data. So that's what a scatter plot is. It's dots that represent data, to be exact. Now on this 229, there are questions 1 through 5, and I am pretty sure that you can answer those questions based off of your knowledge from lesson 26. So I want you to hit pause and answer questions 1 through 5, and then come back and check and see if you're right. Answering these questions, number 1, what is the independent variable? Well, remember the independent variable is always the x. So if you look at the horizontal axis, you see that that is represented by the months after January 2009. Now, hopefully, you notice, so since this is the month after 09, this right here represents January of 09. 12 months later would be January of 10, then January of 11, right? Because for every 12 months we have a year. Number 2, what is the range of values of the independent variables? Well, again, if you look at this, it starts at 0 and it goes all the way to 72. So the range would be from 0 to 72. The dependent variable, hopefully you notice that's the consumer price index. So for the 3rd time this semester we are dealing with, we're playing with the consumer price index. And number 4, what is the range of values that is represented for the dependent variable? Well, that starts down at 195 and it goes all the way up to 230. So those would be the range for the dependent variable. Now, in number 5, it talks about a positive trend when as one variable increases, the other variable also increases. A negative trend is when one increases, the other decreases. And using the names of the two variables from this scatter plot, describe the kind of trend. Well, if you look at it, as the months increase, also the CPI increases. So that would be your sentence. So my sentence could be, as the number of months after January 2009 increase, the CPI also increases, and therefore we have a positive trend. So this positive trend is, similar to slope that we talked about in our last pages. We also talked about relative and absolute change, and when we talked about those, we talked about positive or negative and how that looked in terms of increasing and decreasing. So all of these concepts are very much related. So if you learn one, hopefully that will make the others easier. Moving on to page 230, we've got the same graphic, but now notice we have this black line that cuts through. That black line is called the trend line, also known as a regression line. So we have ourselves, there's our linear model, y equals 0.3812x plus 202.29, so that's important to reference. And what this does is it gives us a constant change, right? Because with that we have a slope. Slope is the constant change over time. And this allows us to predict for the future. If we have that, varied mess of dots that is our scatter plot, we can't really do any predicting from that. But when we have a constant change, which is a trend line, that then allows us to make future predictions. So from that, hit pause. And I want you to do 6 through 9 and stop. 6 through 9 and then come back and check out your answers. So in number 6, the slope of our model is 0.3812. And remember we talk about, if slope is easiest to interpret if you put it over 1. So remember on top we have our y values and on the bottom we have our x's. Well, the y's, if you recall, are CPI and the x's are months after January of 09. So when you look at it that way, you can think, well, see, they're both positive, so they're both increasing. So my CPIs, let me change color here for fun, my CPI will increase 0.3812 for every 1 month after January of 2009. Let me type that up for you. And so you want to, one, have that word increase or decrease, right? Because our slope is positive, we have an increase. And then make sure you reference what are your y's and what are your x's, your independent, your dependent variable. Those should be represented in your statement because that's what your slope is all about. In number 7, what does the model predict for January of 2009? Well, remember on your graph that January 2009 has an x value of 0. So I will take my equation, y equals 0.3812, plug in the 0 for x, and add 202.29. This is the kind of math I want to do, right? Because you multiply anything by 0, you get 0. So I end up with just y equals 202.29. So in January of 2009, the CPI was 202.29, right? We also call that our y-intercept, because remember, the y-intercept occurs when x is 0. Moving on to number 8, what about January of 2014? Well, that's 5 years later. 5 years is the same as 60 months. And therefore, x is 60 because it is 60 months after January of 2009. So I'm going to have y equals 0.3812 times 60 plus 202.29. So you do the math, and if you do it well, and I hope you do, you end up with 225.162. So the CPI, this is again an estimate, for January 2014 would be 225.162 based on our linear model. And the actual CPI in January of 2014 was 222. Okay, so our estimate was 225.162. They're telling us the actual was 222.247. So should the linear model give the actual value? And hopefully it's pretty clear and you quickly say no, because the model is an estimate. That's why we call it a model. It's not exact. If we wanted exact values, we would just deal with the scatter plot. So we do have ourselves a model. A model is an estimate. Sometimes your estimate is going to be high. Sometimes your estimate is going to be low. It is an estimate. It'll be close, right? 225 is pretty close to 222, so we're not too mad about that. All right, moving on to the bottom of page 230, we see the next beautifulness of this page, and that comes in the term of the scope of the model. So when we talk about the scope of the model, well, let me back up a second. If we were going to predict data, right, it would not make sense. We're in the year 2015. It would not really make sense to say, I predict the population of the world to be 830 billion in the year 4000. How do I know that, right? It's so far out. So the scope of the model kind of talks about what is a good length of time to be able to predict. So because we don't know, there are so many variables that affect change, we can only predict out a little bit, a couple of years, maybe 5 or 10 years in the future, or 5 or 10 months, depending on our data. So the scope of the model always refers to the x-axis. So we don't, well, you could also talk about the independent variable. So independent is what is dealt with in terms of the scope. So when we go back, and yes, I'm going to do this to you, I apologize. When we go back to this graphic, you can see pretty clearly that the data ends right here, which I would say is probably right around 62. We don't want to go much farther out than maybe a year. So, 72 is the end of this picture. So 72 months would be a good scope, 0 to 72. We can estimate any time in there. And obviously we know from 0 to 62 we have that data. But we could use this model to predict this far out. So when it talks about, where am I at? The scope of the model, I would probably say 0 to 72 because that's what's shown on the graph. And that's another 10 months past where we are now. You don't hear IBM or any other big company, predict profits or losses for that matter, 4 years in the future. They usually talk about for next quarter or in the next 2 quarters. They're very short-term predictions because too many things can happen when you get too far out. So we want to be pretty close. So I would say you're safe by saying the scope of the model is from 0 to 72. And notice that that matched our the range of values for our independent variable there on page 1 of this lesson. Now, would it make sense to estimate the CPI in the year 2030? Well, we started this data in 2009. If we go to 2030, that's 21 years times 12 months in a year. That's 252 months. We said the scope of the model would be good to end at 72, maybe 74 if you were feeling frisky, but 252, no. That is way too far outside the scope of this model. It's not even on the edge of possible. It's just way too far out there. So you want to make sure if you are doing a prediction that you are well within the scope of your model. Moving on to page 231, the linear correlation coefficient. This is noted by the letter R. I know it doesn't make sense. That's, CC, correlation coefficient, and yet we're using R. This is the Pearson correlation coefficient is also how it's known, depending on what math book you look at. And it's always been R. I mean, I don't know why. If anybody can tell me that, I'll give you a high five. So let me know if you figure it out or you do some research on that, because frankly, I just never have. So if you look back at that graph, nope, that's not what I wanted. Again, I'm going to make you seasick here. You'll notice that right here, they tell you that R squared is 0.9591. Now, R squared is used, I'm not really exactly sure how to explain this best without being able to talk to you and have a full conversation about it. But basically, it talks about the line, right? This line, and the steepness of it, the perfection of it is what, steepness is not a good word, perfection. That's what I want to say. So the linear correlation coefficient talks about the perfection of your data. And again, this would be easier to talk about in class because I can point to things a little more easily. But if we have data in our graph that is like this, and then your line goes here, notice that I have data way far away from my line. So this would have a very low linear correlation coefficient because my data is not very linear. So my data is not very perfect in terms of being close to the line. Now, if I have data that looks like this in my linear correlation coefficient, notice how all my data is very, 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 very close to my line. I have the perfection of my data, right? It's almost perfectly linear. This is going to have a high linear correlation coefficient. Okay, and we use the R squared to figure out what we have. So I ran out of room. R squared is going to be a number, right? Let's just say it's 0.9. Then, how do you go from R squared to R? Well, if we take the square root of both sides, then I'll get R equals, and the square root of 0.9 is 0.95, rounded to 2 decimal places because I'm out of room. So if you have 0.95, okay, fantastic. What does that mean? Well, let's turn the page, turn this page. This talks about the scale of the linear correlation coefficient. It is always going to be from -1 to 1, right? So you can see here in the middle, this hot mess. There's data all over that doesn't really show a positive trend or a negative trend, and therefore you have no linear correlation coefficient. It's 0 because it doesn't really predict a line. Whereas in the other two, right, if you go, let's look to the right here first, notice how these trend lines are negative, right? They're going down. That's why you see you have a negative R, because your linear correlation coefficient is going to be negative because you have a negative trend. The more perfect your data, right? So if you look at this one all the way on the right, see how perfect this data is? I mean, it is perfect. All of your dots show exactly on your trend line, and that means you have a perfect line. The linear correlation coefficient is -1. Whereas way over here on this side, I have a positive trend. My data they're going up, and therefore I have a linear correlation coefficient of +1. So the closer you are to 1, the more perfect your data is in Becky terms, in terms of perfection. Okay, so you can see in this graph here, difference between positive and negative correlation. Positive correlation has a positive slope, and your correlation coefficient is going to be between 0 and 1. If it's negative, it'll be between 0 and -1. So you do have to pay attention to, okay, I have a negative, because R squared is always going to be positive, always. So when you take the square root, you're going to have to decide if you're going to put a negative in front of it or not based off of your data. So if you have a graph, let me change colors. If you have a graph that looks like this and your line is going down, then you're going to want to make sure when you take your square root of R squared that you throw a negative in front of it, because your data is obviously decreasing. So that's kind of something to practice with and see what, the more you do it, the easier it gets, and it makes sense. So on page 230, we have that graph, and we're going to use it. So the linear correlation coefficient for the CPI over time. Well, hopefully you notice that they tell you on there that R squared is 0.9591. That's not the linear correlation coefficient, that's R squared. So we have to take the square root of both sides, because the square root of R squared will give me R, and the square root of 0.9591, I'm going to round to the 4 decimal places, and I get 0.9793. Now this is positive because if you remember from the trend line, it's going up from left to right. They both increase. And when we look into number 13, do you think this linear correlation coefficient indicates a good fit? A good fit means we have a strong correlation. The closer this is to 1, the stronger the correlation. So if you round to 2 decimal places, you're at 0.98. That is very close to 1. And so yes, we have a strong positive, I'm going to throw the word positive in there, strong positive correlation. That means our data is very close to being a straight line. It's not perfect, because if it's perfect it would be 1, but it's pretty close to perfect because it's 0.98. So we have a very strong positive correlation. If we write a sentence explaining what this means, well, what does it mean? Well, it means there's a strong correlation. There is a strong, I'll even throw the word linear in now, strong linear correlation between the number of months after January 2009 and the consumer price index. That's what it means. Now in number 15, does that mean we can say there's a cause and effect? Do the number of months after 2009, does that affect the CPI? And the answer to that is, I'm going to say almost always going to be no. Correlation does not predict causation. And that's going to be something that you want to make sure that you really pay attention to. Just because two things are linear, positive, they're correlated, they have a positive correlation, that doesn't mean that one predicts the other. So, if we would do a graph in class about eye color compared to shoe size and run some tests and find that we have a 0.98 linear correlation coefficient, that doesn't mean if somebody walks in the door, we can say, oh, they have blue eyes, they must wear a size 8 shoe. No, they have nothing to do with each other. Just because our data shows that we have a positive linear correlation, that doesn't mean that one causes the other. So correlation does not predict causation. Never, ever, ever. Make sure you remember that, because that question will come up. You have to make sure you're paying attention and understanding that just because we have correlation does not mean we have causation. And that is the end of the first video for lesson 26. Come back for number 2.